are going to start with alpha particle scattering experiment. So as we have already learned that this is the experiment which is very important for the discovery of atomic model given by Rutherford. So Rutherford was the person who had proposed, he had instructed, and H. Giger and Marston, they are the two scientists around 1911, they had done this experiment, which is alpha particle scattering experiment. So first let's see what is this experiment, and later on we can analyze the observations, and we can see how from those observations Rutherford's atomic model was developed. So coming to the experiment part, here you see this is a lead cavity. Inside the cavity there is this source where the bismuth of 214 and 83, the bismuth is kept, and this alpha particles are then bombarded to the foil, right, to the gold foil. So here we have gold foil. From the source alpha particle would come out. So alpha particles are nothing but the helium particles which has two atoms, and they are coming out from the source with energy 5.5 million electron volt. So that amount of kinetic energy, they would just come out from this source, and they are going to hit the foil, which is the gold foil kept here. So gold foil is is nothing but a very thin foil, so that there are if it is not very thick, then the alpha particle don't have to penetrate much. It's a very thin foil, so that it can directly hit the gold atom. So this experiment does do what? It just hits the gold foil with the helium ions or helium particles, which are alpha particle, and then there is a zinc sulfide screen, and in the screen there is the bright flashes that comes out whenever the alpha particle hits the gold foil. There is a flash that comes out which gets captured in the zinc sulfide screen, and this bright flash that comes out, this is called scintillation. And through the usage of scintillation, you can see where after hitting the gold foil, where is this alpha particle getting scattered. So when this alpha particle, after hitting, which direction it is going, after colliding, which direction is the alpha particle moving, that is captured by this zinc sulfide screen. As you know that when collision happens, after collision things moves in different direction. So based on the study of this collision, of this collisional effect, and we finally, after scattering, which is the angle at which these alpha particles are getting scattered, based on that the whole study was done, and the atom of gold was, having a kind of picture, so that the whole model of atom was kind of picturized or kind of created by Rutherford. So let's see what was the various observation that was seen from this experiment. So from the source, as the alpha particles are hitting, so after hitting the foil, if it scatters or it moves in different direction, at that particular angle it will make a bright flash which will be captured by the zinc sulfide, and this whole flash would be captured by a collimator or microscope collimator. So whichever angle it is making from its initial position, suppose this is the initial position direction of alpha particle coming, and after hitting, whichever angle it moves, that angle from its initial angle is marked as theta, and this angle is called the scattering angle. As to from the initial position, what is the angle by which it is getting scattered is called the scattering angle. So it was found that most of the alpha particle was just passing straight, and it was not getting hit, or it's not getting collided by anything. So most of the alpha particles just went straight and hit it just hit the zinc sulfide screen. So it means that most of the particle did not collide with anything in the gold foil. Only 0.14% of the total scattered, like most of it didn't get any scattered, it just went. And how many ever got scattered? Out of that, 0.14% of the scattered alpha particle had the scattering angle more than 1 degree. It means that rest of this particle which even got scattered was not even scattered by 1 degree. So only 0.14% was scattered more than 1 degree. It means that there was a more than 1 degree scattering. Rest of the scattering was very negligible, not even a degree scattering was done. And majority of particle didn't even get scattered, it just passed through. And out of 1 by 8,000, that means out of 8,000 scattered alpha particle, only one particle was scattered more than 90 degree. It means that how much ever particle got scattered, among them only 0.14% was kind of we can read the scattering, which is more than 1 degree, at least some scattering. Out of that, you can see that there are very negligible number of scattered alpha particle had the scattering more than 90 degree. And the amount is 1 by 8,000. So out of 8,000 scattered alpha particle, only one was scattered in 90 degree angle. So this is the graph. If you take the scattering angle as the angle gets increase, you see most of it, highest number of the alpha particle just did not get scattered, or even if they got scattered, it's very less angle, not even a degree, and only few were more than a degree, and then higher the degree, more than 90 degree was very few. So numbers are very less as you go increase in the scattering angle. So this was the observation and the experiment of the alpha particle, and in the next video we will see how from this observation what kind of conclusion Rutherford made, so that it helped him to come into the conceptualization of the Rutherford atomic model. But nonetheless, this experiment remains a very important experiment when we study about atomic theory, as well as when we study about nuclear physics. This from both point of view, because this gives us concept of the nucleus inside the atom and all other subatomic particle, and therefore for the subatomic studies, this experiment remains very important.
If you like the video, then press the like button, subscribe to the channel and press the bell icon.